So, hello students, welcome to this lecture on the subject of advanced semiconductor devices KEC 056. This is lecture number 12. I am Dr. Raman Kapoor, Associate Professor at ABS Engineering College, Ghaziabad. In today's lecture, we are going to continue our discussion on PN junctions, which we started in the previous lecture. Okay. So, let us continue. In today's lecture, we are going to start with what is known as capacitance in the depletion layer. Okay. Just to give you a quick summary, in our previous lecture we had introduced the concept of depletion region. When holes diffuse from P to N, electrons diffuse from N to P, they recombine at the junction, uncover immobile ions, that results in the formation of depletion region. So, depletion region is depleted of free charge carriers, only has immobile ions, negative acceptors on P side, positive donors on the N side. Okay. Since there is some accumulation of charge inside the depletion region via ions, there is no availability of free charge carriers. The P side has free charge carriers, the N side has free charge carriers. So, this is similar to a scenario where there is a some kind of sort of a capacitor is there. Okay. So, two conducting plates separated by a dielectric material, which basically means that the depletion region will have some sort of a capacitance associated with it. Okay. And capacitance, as we know, can be defined as rate of change of charge with respect to rate of change of voltage. Okay. So, change in charge with respect to change in voltage. You apply a differential voltage across a capacitor, some charge gets deposited on one plate, equal and opposite amount of charge gets deposited on the other plate. This difference in charge or diffusion charge or depletion charge, you can say here, divided by the change in voltage, this is nothing but capacitance. Generally, we measure it as per unit area, and when we measure it at per unit area, we write it as epsilon by WD. Okay. So, say for a parallel plate capacitor, when you write the capacitance, it is equal to epsilon A by D. D is separation of plates, A is area, epsilon is the medium. Here we use epsilon S, the relative permittivity of the semiconductor. If it is silicon, you use the dielectric constant of silicon. WD is a depletion region width. We have already derived the expression for depletion region width in our previous lecture. Okay. So, again this is the incremental charge, depletion charge on either side of the junction, on the P side and N side of the junction, and incremental voltage, applied voltage dV. Okay. So, the depletion region width, we have already seen the expression in last lecture. This is where we basically ended our last lecture. Okay. For a junction, if we have equal doping on either side, so I am saying that Na is equal to Nd. Whatever is doping is there on the P side, the same doping is there on the N side, only the magnitude. Okay. So, the magnitude of Na is equal to magnitude of Nd. Let us make it equal to N. Okay. So, you can use either value, you can use Na, you can use Nd. So, if I replace Na and Nd with N here, this is going to be 2 times N, this is going to be N square. Okay. So, this is going to be my equation for that type of a depletion region where there is equal doping on either side. Such type of a junction, because the ratio of depletion region width is inversely related to the doping, okay, because Na and Nd are equal, which basically means that Xp and Xn are also equal. So, the total depletion region width Wd is going to be equally distributed on the P side and the N side. Okay. So, for a junction with equal doping on either side, this is your depletion region width. Okay. V naught is built in potential, right. So, your depletion layer capacitance becomes equal to this value here. Okay. So, epsilon S by WD. So, this is the value which you are going to get. Okay. Under the influence of applied bias, so if you now apply a voltage across, because whenever you apply voltage, that is when you are going to deposit the charge only. Okay. This voltage applied is basically in opposition or it subtracts itself from the built in potential. If you apply a positive potential or a forward voltage, the net potential barrier is going to reduce. So, V naught minus V is going to be a lower number. If you apply an opposite bias, a negative bias or a reverse bias, it is going to add up. So, V can be positive, V can be negative. This applied bias can either be positive or negative. So, V naught minus V can either reduce or it can increase. Okay. So, V naught minus V will depend upon how much bias you have applied. This basically means that your diffusion or depletion layer capacitance takes this form, right. If I square both the sides, I can obtain this expression here. This is just obtained by squaring both the sides of this equation. Okay. So, dV by dCd square can be written as this expression here. Okay. This basically means that if I plot, okay, this expression basically tells me if I plot a graph between V and 1 by CD square, you might get a straight line, okay, because of this, because you have a minus sign basically there, the graph might fall as well, it become more negative when you reduce it. Okay. If you take the slope of this kind of a graph, it is going to help you in obtaining the doping concentration. Okay. So, from where did we start? We started from a junction, from a PN junction where there is equal doping on either side. We use the expression of depletion region width. We defined capacitance per unit area just for the depletion region itself. Okay. Introduced an applied bias. In that case, a graph between 1 by CD square and V is going to be a straight line, and the slope of this line can be used to estimate the doping concentration. Now, since we have said that the doping is equal on either side, so if you get the value of n, you basically get the value of doping on both the sides. Okay. Let us proceed further. We now want to see, since we have introduced the concept of applied voltage, if that applied voltage is forward or positive, it reduces the potential barrier. If it is negative or reverse, it increases the potential barrier. This built-in potential barrier is what basically stopped diffusion of charge carriers across the PN junction. If the net value of this built-in potential is changing with applied voltage, it basically means that the current which can be obtained from a PN junction is also going to be different, right. So, to see a equation or to obtain an equation and to get the graph, we need to understand how the IV characteristic or the current voltage characteristic of a PN junction looks like. Okay. We make a few assumptions, and these are fairly reasonable assumptions, they help you to ease the mathematical analysis. Devices are generally associated with a lot of mathematics, and some assumption which are quite reasonable help you to ease that analysis. So, again we say that the junction which we have, the depletion region or the PN junction which we have, has an abrupt junction. We immediately transit from P to N or N to P. There is no gradient, there is no grading of doping density. Okay. The depletion region has abrupt boundaries. You can immediately transit from P type to N type to P type. In the bulk, there is neutrality, there is no electric field. Okay. Another approximation is known as Boltzmann approximation, which basically says that either it is on the P side or the N side. The Fermi energy level EF is at least 3 kT from the band edges. Okay. So, in N type it is 3 kT below EC, in P type it is 3 kT above EV. Okay. This basically helps you to avoid thing known as a degeneracy, because if Fermi level moves inside, that is a degenerate semiconductors, and then your analysis turns slightly different. Okay. Next is a very important assumption, and this basically forms the basis of our analysis of a IV characteristic of PN junction. Whenever we are making holes to move from P to N, or we are making electrons to move from N to P. This is possible by applying a certain voltage across the p-n junction. Whenever we do this, we are injecting minority charge carriers. Why minority? When holes move from P to N, in the N side they become minority charge carriers. Whenever electrons move from N to P, inside the P region, these electrons become minority charge carriers. This phenomena is known as minority carrier injection. The level of minority carriers injected on either side is generally, for all practical purposes, very small as compared to the majority concentration which was present originally. Okay. So, in the P side you had majority holes, in the N side you had majority electrons. Whenever you inject minority carriers, whenever you inject more holes on the N side or more electrons on the P side, the concentration of these injected carriers, the magnitude or the concentration is quite small as compared to the original majority concentration. Okay. So, holes injected in the P side, that concentration is very small as compared to the majority hole concentration in P side. Hole injected in the N side, that injected concentration is quite low as compared to the majority electron concentration in the N side. This phenomena is known as minority carrier injection and the magnitude is low. Okay. So, we are not inverting the semiconductors on either side, we are not reversing the doping, we are just generating excess charge carriers on P and N side via an external electric field, so that current starts to flow. Okay. This phenomena or this condition is known as low level injection and it is quite critical to obtain the expression for IV. Okay. Next we say that inside the depletion region there is no generation or recombination. Okay. The electron and hole currents are constant throughout the depletion region. There are some special purpose diodes where some energy is made available inside the depletion region, and because of that some charge carriers may be extra produced, maybe some extra generation or recombination, but our objective is to obtain the IV equation of a p-n junction. So, for us there is no generation and recombination inside the depletion region. You are just injecting holes from P to N, electrons are being injected from N to P. Using these assumption, we now proceed further and now we want the IV equation for a p-n junction. This equation is known as Shockley equation. Under externally applied bias, holes can diffuse from P to N, electrons can diffuse from N to P, okay, and this diffusion current constitutes diode current. Now, whenever we are saying diffusion of holes from P to N or diffusion of electrons from N to P, this is what is known as forward condition or forward bias condition. Okay. Because this diffusion only occurs when you reduce the potential barrier, and that is possible when you do forward biasing. Okay. In reverse biasing, this diffusion does not happen, minority carrier drift current is obtained. Okay. The diffused charge carriers, this is termed as minority carrier injection, which I have just explained in the previous slide. This is in excess to the original equilibrium concentration. So, you had doping on P side and N side. So, you had some equilibrium concentration, but now you have basically added some excess charge carriers, the so called phenomena of generation and recombination of charge carriers. Okay. So, now let us derive this expression for diode current or what is known as Shockley current. Okay. Just look at this graph for once. See, this is your junction. Okay. This is the P side. So, the edge is denoted as minus xp and the N side is denoted as plus xn. Origin is considered as the junction. Okay. So, here if you see, this has been divided into two parts here, because we are saying that in the depletion region there is no current, okay. There is no generation or recombination. Whatever current is produced, whenever holes reach here, they diffuse here, from this edge onwards they produce some hole current. electrons diffuse here, from this edge onwards they produce electron current. The holes which were diffused from P to N, minority carrier injection, this starts to produce hole current. Electrons which were injected from N to P, this starts to produce electron current. These are excess charge carriers in addition to the equilibrium concentration. Okay. So, this is the source for producing current in a PN junction, right. Let us just see the mathematics of it now. We start with our expression on built-in potential. So, this is your V naught built-in potential. At thermal equilibrium, when there is no bias present, this is the expression we have seen it in the previous lecture. I take exponential on both the sides to get rid of this natural log. P subscript P is hole concentration on P side, P subscript N is the hole concentration on the N side. Okay. V naught is built-in potential, this is Boltzmann constant, temperature and Q, right. When you have applied a bias V, now V can be positive, negative. If it is positive, forward bias, if it is negative, reverse bias. If it is positive, V naught minus V reduces, barrier reduces, diffusion can happen across. If V is negative, V naught minus V increases, only minority carriers can drift across. Okay. So, when we have biased, hole concentration at x equal to minus xp, the P edge of the depletion region, divided by hole concentration at xn, the N edge of the depletion region. To the right of xn current flows, to the left of minus xp current flows. Okay. This is the equation you are going to have. Okay. So, let us just label these as 1 and 2. Excess hole concentration at x equal to xn. Why xn? Because holes are injected from P to N. So, from xn onwards, this is the excess hole concentration, okay, denoted by delta, holes in N side, number of holes per unit volume in N side. This is equal to whatever is total concentration present minus the equilibrium concentration. Okay. Let us just call this as equation 3, you can call this as 4. This is nothing but excess electron concentration at x equal to minus xp. Okay. Why minus xp? Because electrons are being injected from N to P. If I divide 1 and 2, so I divide 1 by 2, this is the equation which I am going to get. This is obtained by dividing 1 and 2. Okay. Now, see here that this P subscript P, holes in P side and holes at minus xp is basically the same thing, because majority concentration is not altered whenever you do excess charge carrier generation. Okay. The only percentage increase you see is in the minority charge carriers, right. So, if you add holes on the P side where they are already in majority, it is not going to make any difference, okay. Because if there are lot of holes present, you add a small amount of holes, remember low level injection, that relative increase is negligible. So, they are almost equal. So, holes in P side at equilibrium is equal to holes at minus xp when biasing is applied. So, that term is going to cancel and you are only going to have holes at x equal to xn divided by total number of holes per unit volume in N side. This is equal to exponential of QV by KBT. V is applied bias. Okay. Similarly, this expression here delta Pn, now I substitute 5 in 3. Okay. So, you substitute equation 5 and 3 and 5 in 4, you are going to get these equations. Okay. So, this is the excess hole concentration at x equal to xn. This is excess electron concentration at x equal to minus xp, right. So, these are the expressions which you are going to get for excess carriers which you have injected, holes injected from P to N, electrons injected from N to P, right. At any point x, now I am not talking about xp or xn, I am just saying at any point x, total concentration is equal to equilibrium plus excess. Whatever was present at equilibrium, then you applied bias, you created excess charge carriers. So, equilibrium plus excess is the total concentration with respect to distance. Total electron concentration with respect to x is equilibrium plus excess. So, this is at equilibrium and this is the excess. Okay. Del P naught is at x equal to 0, how many excess charge carriers were generated? E to the power minus x by L P. Similarly, delta n 0 at x equal to 0, how many excess charge carriers were generated? E to the power minus x by Ln. Lp Ln is the diffusion length, the amount of distance travelled after diffusion from the edges. Okay. Again, I will show you this image again. We are interested in hole current from this edge onwards. We are interested in electron current from this edge onwards. Okay. So, this is where the injection has taken place, excess charge carriers start from here. So, I split the p-n junction into two parts. Now, instead of x, I define two horizontal axes, one is xn, another is xp. xp is x axis on the p side, xn is the x axis on the n side. Okay. So, now my expression for excess carrier concentration changes, excess electron with respect to xp. Now, this is not at x equal to xp, but with reference to an axis known as xp on the p side of the depletion region. Similarly, excess holes with respect to xn is equal to this expression. Okay. This is excess holes injected right from the edge of the n side. This is excess electrons injected right from the edge of the p side. Okay. Using my previous few equations, you can easily see that this is the expression which you are going to get for your excess charge carrier, excess electrons, excess holes. These are the excess electrons from this point onwards. From this point onwards, whatever excess electrons you have. This delta p xn is the excess holes from this point onwards. This is going to produce current. Okay. So, these two expressions, now I am going to use total hole current injected into the n side is nothing but current equal to area times current density. Current density is current per unit area. So, current is equal to current density into area. A represents area here, and since this is diffusion of charge carriers, I am going to use hole diffusion current. Okay. Total electron current injected into the p side is area times electron diffusion current density, right. So, total current injected across the p-n junction, holes from p to n, electrons from n to p, is equal to hole current at x n equal to 0 plus electron current at x p equal to 0. So, this equation, these two equations will be differentiated, this with respect to x p, this with respect to x n. Whatever comes, you put x n equal to 0 and x p equal to 0, and this is the final expression you are going to get. Okay. This is the total current across a p-n junction. I combine the common terms. Okay. This is the common terms I am going to get, and this is an exponential term. This is known as I naught, and this is known as reverse saturation current. This is the current which flows across a p-n junction when reverse biased. Okay. Because of this equation, because of this Shockley equation, if V is positive, exponential term is very high. Okay. So, this is going to be like exponential of, okay. So, this should be exponential of V by V t minus 1. Okay. Whenever V is positive, exponential term dominates. Whenever V is negative, exponential term is very low as compared to 1. Because of this, we obtain the most important application of diode, which is the application as a switch. When V is positive, you get exponential forward current. When V is negative, you only get a constant very close to 0 current known as reverse saturation current. That is why, because of this Shockley equation, the IV characteristic of a diode looks something like this. Okay. Finally, since you are biasing this diode, there is conductive P region, conductive N region on either side, okay, consist of a depletion region in the middle. So, you have P type region, you have N type region, there is a junction and there is a depletion region. This is similar to a parallel plate capacitor. So, you have P here, you have N here and you have a dielectric in the middle, nothing but your depletion region. So, under the influence of external bias, you can obtain two different types of capacitances from a PN junction. In forward bias, we obtain what is known as diffusion capacitance, defined as rate of change of forward charge with respect to forward bias. Charge is time into current. This tau is carrier lifetime. Okay. So, whatever you have diffused, the time for which it remains before recombining, that is carrier lifetime. Okay. IF is equal to this, exponential term is high, 1 reduces. So, your diffusion capacitance is equal to this. In forward bias, when voltage increases, current increases exponentially. So, since IF is directly proportional to Vf and C diffusion is directly proportional to IF, which basically means diffusion capacitance increases with increase in forward bias. Okay. In reverse bias, we measure what is known as transition capacitance, which is measured per unit area and written as epsilon S by WD. This is relative permittivity, this is depletion region width. When you increase reverse bias, you increase Vd. So, Vr reverse bias increases, depletion region width increases, which basically means that transition capacitance reduces. So, in forward bias, capacitance increases with applied voltage, in reverse bias capacitance reduces with increase in applied voltage. Okay. So, these are some of the references you can refer to for the content covered in this lecture. We have covered a very important topic known as Shockley equation and diode capacitances. In forward bias, you get exponential current, in reverse bias, you get 0 to constant reverse saturation current. This is why a diode is unidirectional, it works like a switch. Okay. So, we will continue our discussion in the next lecture. Thank you for now.